Okay, good. So I requested you to think of things that you want to ask in this class, so that we can also have some participation. The other day I screwed up a very simple formula, and so let me just write that one more time. So that was for the pseudoscalar and vector pseudoscalar and vector mesons are splitting. So this was 1 minus and this was 0 minus, and the formula was j squared minus s1 squared minus s2 squared, like that. Okay, let's put a arrow on top like this. So this was j times j plus 1 minus s times s plus 1 times 2, because they are both, and s equals half. So you have j times j plus 1 minus 2 times half times 3 by 2. So that's j times j plus 1 minus 3 by 2. So for j equals 0, you get a minus 3 by 2, and for j equals 1, you get a plus half. So the ratio of the splitting is like this. So this is delta over here, and delta like this, and this is 3 delta. This is the same formula that also showed up in the hyperfine splitting and in the 21 centimeter line. So this is the same kind of formula showed up also in 21 centimeter line in hyperfine splitting. Anyway, I have given you a small set of problems to work on, so that you can start to fix some of these ideas in your minds, and so that you learn to do a little bit of this kind of algebra. Okay, so that's the key thing, that I can be screaming at the blackboard till day's end, and there's no point to my doing that. So so where we left off the other day was in electron proton scattering, and we said that this must have the form L mu nu times, let me call it H mu nu, for the hadron part, and we saw an explicit form for the L mu nu, so which was 2 times P1 mu P3 nu plus P1 nu P3 mu plus G mu nu, and this comes from doing the spin sums and all that, introducing spinners and doing the spin sum. So it's very straightforward, and you can trivially check that Q mu L mu nu is equal to 0, which is what young Aman was trying to help us with the other day. On the other hand, this hadronic part, if it is not Dirac, if this is not Dirac particle, the most general 2-rank tensor that you can write down, symmetric, is K1 G mu nu like this plus K2 by. So this is trivially respected. Trivially respected. So this is K2 P nu like that plus K4 by MC squared. We wrote this Q mu Q nu plus K5 by MC squared times P mu Q nu plus P mu. So this is the most general thing. So on this you impose current conservation, which is that Q mu H mu nu equal to 0. And if you impose this, then you will see that not all are independent, and K4 and K5 are not independent. K4 and K5 are not independent, and this of course is one of the homework problems, to find the relations between K1, K2, K4 and K5, and it is sure to show up in your final exam, so you better work it out. See, it's a very simple course. You even know 2 months in advance what's going to be in the final exam. So we saw that at the end of all this, if you impose this, impose current conservation, etc., then you will end up with only two independent functions which you can choose to be k1 and k2. Okay, there's nothing which says that you can't choose k4 and k5, then it will be re-expressed in terms of k1 and k2. Okay, so we choose k1 and k2 to be the two independent functions. And if you do that, the square of the matrix element is what we wrote the other day, m squared, spin sum and all that, 2qe squared divided by q squared, squared like so. In this k1, remember that the ki are all functions of only q squared, nothing else. k1 of p1 dot p2 minus 2 mc squared like this plus k2. You know, these are all actually extremely beautiful expressions, and if you do them either by hand or by using whatever it is, p3 dot p4, I guess, if you use it, do fine calc and all these things, you know, it's really great that you can see all these expressions coming to life. Okay, so it is all up to you. Yeah, sorry, some question. QE, GE, oops, GE, this is the, yeah, charge, GE. My handwriting is disgraceful, that's all I can say. It's all the fault of modern technology. Of course, very easy to blame others for one's own inadequacies, but anyway, that's how it is. So then we wrote, finally, we wrote d sigma by d omega, Rosenbluth. Now please do this, please do this. Take the EMU notebook given by Romao and make the corresponding changes and prove to yourself that you are actually capable of doing this. Now, if Rosenbluth could do it in 1950 without Mathematica, surely you can do it in the year 2025 with Mathematica, right? So this is alpha h bar divided by 4me sine squared theta by 2. This we know, this looks like the Rutherford thingy, e prime by e, and this we said is in the lab frame. Lab frame is 2k1 sine squared theta by 2 plus k2 cosine squared theta by 2. Note that for elastic scattering, E prime is not independent of E and cosine theta. Very important. E prime is not independent. It's fixed if it is elastic. And it is fixed by this relation. E prime is equal to E divided by whatever it is, 1 plus 2E by mc squared sine squared theta by 2. This is extremely important because when it comes to inelastic scattering, there is no relation between E prime and E. E prime is allowed to be free, okay? It depends on, so if it is an inelastic process, what you do is you measure an inclusive cross section, okay? So you don't know what is the other junk that is produced. All you know is that your incoming electron comes in as a beam and you have a detector which sees the outgoing electron and measures its energy E prime, okay? And if you find at a certain angle theta where you have your little telescope with which you're looking at the electron, okay? So your theta is already fixed. You know what it is because that's where you're observing. And then you measure the energy E prime, and if it does not obey this relation, then you know that the process is not elastic, okay? That is how you discover that the process is not elastic. So this is what we did the other day, but it is customary to rename these things and write down so-called electric and magnetic form factors, where k1 is defined to be minus q squared gm squared and k2 is 2mc squared GE squared minus Q squared by 2mc squared GM squared. So you may start to wonder, and of course it's natural to wonder, why are there so many definitions? Because this is a long and historical subject. Many different people have studied it many different times. So different authors at different times introduce different things, and there is a particular purpose for which a certain author introduced it for a certain purpose. Today, of course, we have an integrated picture, and we know what all these things are. And as a homework exercise, I'm going to ask you to find out what is meant by the Pauli form factor. Pauli, you heard of Pauli? Wolfgang Pauli. So he used to do these things also. So there's something called the Sachs form factor. Who is Sachs? No idea. Sachs and Pauli form factors are related to these things, and you find out the precise relationship between these two things. Now I want you to look at figure 8.5 in Griffiths. Whoever has the Teams link can open Griffiths and then share with the others. Okay, yeah. So who's got? You got it on your phone. This guy has it on his laptop. Okay, so he's going to share it, and then we are going to see what is in it. Yeah. You have to set up a Teams meeting first. You have to boot your computer first. Okay. So these are called the magnetic moment distributions. Teams. Can people see his screen? One sec. So SS is inviting you. Okay. AS is already there. So that's good. Who is AS? Let's mute it. 8.5. That we saw already the other day. Oh, that one. So let's make it big. So what does it say this is? Is the proton elastic form factors apart from an overall constant, the electric and magnetic form factors. So this is for the proton. Okay, GE and GM are practically identical and at least up to 10 GeV squared, and are well fit by a phenomenological dipole function. Okay, so it's a very simple formula that you see over here. That's more or less what I've written over there also. So you see, so even though, so what is this conveying to us? This is conveying to us the fact that even though the proton is a complicated object, it has 3 quarks sitting in it, and it has a gas of gluons and QQ bar pairs and so on, but its response to the electromagnetic field, after all, what is going on? It's the electron that zips by the proton, emits a virtual photon which excites the proton, right, which is a complicated object. So it's like it's still kind of vibrating nicely. That's what it means, right? So it is having a coherent kind of oscillation in the presence of the field set up by the electron that is zipping by, which is kind of nice. I mean, you don't expect, or actually God knows what we should expect, but certainly not such a simple formula. Okay, so even though the proton has a structure, it has constituents, it has gluons and this and that, the response to the electromagnetic field is as if it is just behaving like a ball of jelly that is just oscillating like that. Okay, that's the way I look at it. But this is only till about 10 GeV squared. Okay, and as long as the collision is elastic. But if you have such a large momentum that is being imparted to the proton, what can happen to it? It can just shatter, right? But of course it shatters, it produces quarks and gluons which immediately hadronize, because strong interaction again pulls any quark and gluon that's produced back and then more quarks and gluons and so on are produced, and what you get in the final state are not quarks and gluons but other hadronic matter. And the simplest thing that it can go to is the excess energy that is imparted to the proton target by the electron is going to produce pion pairs, because those are the easiest to produce. They are by far the cheapest, lightest. So any excess energy will tend to go into pions. It can be 1 extra pion, 2 extra pions, any number of extra pions, provided you conserve energy. And anyway, it's an inclusive cross section. So your detector is only seeing the electron, it doesn't see anything else, right? So that means what it sees is an inclusive cross section. It doesn't matter what the final state was, you sum over all final states. Okay, so this is a physical thing. Whenever you're doing some of this kind of scattering studies, reason you sum over all the final states is you're trying to simulate the experimental situation that your detector is not seeing anything else except the electron. So that means that you have to sum over all the final states. Of course, there's a loss of information, because it would be nice if you had a sophisticated detector and you saw some of the other particles also, then you would have a better resolution of the particular process at hand. Okay, so this is what I wanted to say about this particular thing. Of course, there should be a possibility of getting back electron muon scattering from this. Okay, so we introduced all these additional form factors to say that it's a proton. Supposing it wasn't a proton and this was only a muon, then it must be, this whole thing should collapse to the calculation that you already did. So if it was just point like, then it would mean that this k1 is minus q squared and this k2 is just 2mc squared, and the electric and the magnetic form factors would just be 1. Okay. What is meant by having this kind of a q squared dependence? This means that it is probing the internal structure of the proton. So that's what the q squared dependence here means. But if there's no q squared dependence, that is irrespective of what length scale you're looking at the target, it looks the same. That is to say that there's no q squared dependence. This is because this is only a kinematic factor. Okay, it's not a real q squared dependence. This is equal to 1 means that it's looking at a point like target. So that's what it really means. So this was the review of what we did, and I wanted to talk about deep inelastic scattering. I'll do that on next Tuesday. So in the meantime, I wanted to know if there are any questions, queries, discussions, points that you didn't understand, problems that you tried to do from the first problem set. You got stuck somewhere and you want to ask me questions about that. Rather ask each other questions and see how we are doing about that. Okay. Anything? While you are thinking of what to ask, let me do this RG one more time that we did very briefly in class the other day. I also wanted to show you a demonstration of what unification of coupling constants may look like in the standard model. We had 3 different coupling constants. So that was the screenshot that I sent you yesterday of a calculation that I did, which reproduces a calculation from an old paper by Utpal Sarkar. What's the reason I didn't send you the notebook and I sent you only the screenshot? What's the reason? Very good, so that you do it yourself. No, of course you have the answer in front of you and you have to faithfully type in everything, but when you type it in, then you will know what is what. You'll know what those numbers are and what do they stand for and so on. Of course, if you're really nice to me, then I may also send you the notebook, but most of you are not very nice, so I don't send you. So what is it that we saw the other day that one of you tried to do on the blackboard, and of course it was a bit overwhelming. She's not here today, so let me do it again with this RG equations. So what is the beta function? Anybody? What is the beta function? By definition, beta function for a coupling constant that runs in quantum field theory. Okay, so if G is the coupling constant, then beta G is equal to mu, how the coupling constant changes with mu, like this. Okay, but there's a mu sitting over here, and this is always the definition of the beta function. This is always the definition of the beta function. Am I clear? So if I wake you up at night and ask you what's a beta function, you'll know what it is. Okay? This is very important because there are many different conventions in different books, and you can tie yourself into knots trying to figure out what the different conventions are. If you ever get stuck, this is the definition. Okay? Okay. So in QED, what's the coupling constant of QED? Coupling constant of QED, electric charge, beta E, and that is given by E cubed by 12 pi squared. Okay? How do you know that this is the answer? Well, it's there in textbooks. You can also get it from some of these Romao notebooks. Okay? Romao's 3 one-loop notebooks. What are the 3 one-loop notebooks? What are the 3? Self-energy, vacuum polarization, and vertex correction. If you do them, you will get 3 renormalization constants, Z1, Z2, Z3, and from that you can read off the beta function. Okay? Have you done it? No. You have the weekend in front of you, do it over the weekend. If you don't do it, your problem, not mine. Okay. So this comes from obviously a diagram. So E is Z1 inverse, Z2, Z3 to the 1 by 2, E naught. The 3 renormalization constants which can be evaluated in any regularization scheme. You can do it in cutoff, you can do it in dimensional regularization, you can do it in zeta function, you can do it in Pauli-Villars, you can do it in anything you like. Okay? But the answer has to be the same. Now, Z1 equal to Z2. Z1 equal to Z2. Why? Why is Z1 equal to Z2? Now don't tell me you haven't yet done it in QFT. That's your problem. Again, not my problem. Z1 is equal to Z2 because of gauge invariance. Okay? This is a result of what is called the Ward identity for QED. And this happens to be true to all orders actually. You have to check the statement. But in order to prove the renormalizability of QED, we need to all the time use gauge invariance and properties and a system of Ward identities in order to prove that it is renormalizable. Okay. Z3 in cutoff regularization. Z3 in cutoff regularization is 1 minus E squared by 6 pi squared logarithm of lambda by mu. Okay? And this is what gives us beta E is plus E cubed divided by 12 pi squared, and it comes from this diagram like this. Okay. Now remember when we did the other day E mu scattering like this, E mu scattering, we did this diagram, even this thing was divergent, we had a log piece, and then we redefined the coupling constant GE, introduced something called GR, right? So the fact that there was a divergence is what led us to the requirement of redefining this coupling constant and to re-express the matrix element in terms of the renormalized coupling constant in which the divergence was absorbed. So that's the same divergence that is showing up over here. Okay. Now there are many different ways of getting the same thing, and I'm trying to tell you what is the way in which we did it in the class, and how you get this from some other textbook, and how you would get it from Romao, how you would get it from Stednicki. It doesn't matter. No matter where you do it from, the answer has to be the same. I know that this is an overpowering subject. That's life. It's overpowering for you. It's also overpowering for me. It's also overpowering for Ward, I'm sure, and for Salam, and for Dyson, but that's how it is. Yeah. They are the renormalization constants. Each of the 3 diagrams. unless you download the 3 Romao notebooks, which you will do at 11:31 today. You will download them, you will run them, and you will see what they are. Okay. If you don't want to do it, young Shresh here will download them right now. He will download that notebook and he'll show you, not the notebook, the documentation, and then you show us what it is. Yeah, yeah. Even Dirac didn't know what it meant physically. You just do it because this is the best we can do. Okay. I don't know statistical mechanics. No idea. I have zero fundas in everything, but that's a secret. I have even bigger zero in statistical mechanics. Okay. Now, these things confuse people. That's the reason why I don't do it. Life is hard enough having to figure it out over here. So, okay. So, did you get it? Let's have a look at the, not the notebook. Just get the PDF or the PS of Romao, one loop. Just go to Google, look at Romao, one loop, then download the PS file or PDF. Yeah, first one. Yeah. Now you see, I asked you all to do it yourself, and I know you will never do it. That's why we are using class time to do it. But that's life. Yeah. Share it. What book is this that you're reading? Oh yeah, a very good book. Are you sharing? Okay. Yeah, why don't you open your Teams? Let's have a look. You don't know, that's right. Oh, that's the one. That's the thing, one loop with PV. Yeah. Yeah, vacuum polarization. Scroll down a bit. Yeah. Okay. So there he gets everything that you need. Okay. So you get, so go down. So there is a divergent part. See, he explains everything over here. Okay. Who was asking me? Yeah, here. You were asking me. Look, it's all there. Every single step is done. Okay.
What does Z1, Z2, Z3 each like Z1 is vacuum polarization?
That's what he explains over there. He gives you the explicit expressions for these things. Okay. See, these Passarino-Weltman functions is a basis of one loop integrals, and their divergent parts are explicitly known, and he lists all of them also over there. Okay. In this write up, every single thing is given. Yeah. You don't have Teams? You share with him. Yeah. Yeah. You can't just get it from the air, no? You have to look at it on your screen. Yeah. Are you also on the Teams? Yeah. Does it work? Yeah. Okay. Good. So, if you know how to download these things, you have it on your desktop. How about you? No. No Mathematica? You have. So please download it, and he will be your tutor and you will be his tutor. Okay. So you do it together. You're sitting in the same office, then you find a common place to sit if you're not in the same office. Okay. So you all have to learn to work together. Okay. That's what I'm trying to say, because this subject is so overwhelming, so overpowering. Unless you learn to work together, you will sink individually. Of course, you can also sink together, but who? Ah, yeah. Oh, he's your special tutor. Very good. Okay. See, we have brought him all the way from Germany to be a tutor for you all. Okay. So this comes only from this diagram. Okay. But this is specific to QED, which means that it's a theory with a photon and with one species of electron. Nothing more. That's it. Nothing more. But instead, if you had scalar QED, which would be a theory of, let us say, photon and let's say pi plus pi minus, scalar. Doesn't matter that it's a pseudoscalar, okay, because it's parity conserving anyway. So there the beta function in scalar QED is different. What is it? scalar QED beta E is equal to E cubed divided by 48 pi squared. Why? Because there are two diagrams like this, plus another diagram that looks like this. It's a tadpole diagram which also contributes. Okay, there are two diagrams like this. So here the beta function is E cubed divided by 48 pi squared. What about lambda phi to the 4? Lambda phi to the 4 theory. Also there must be a beta function, and beta for the lambda here is 3 lambda squared divided by 16 pi squared. So there's something funny going on. All the beta functions are positive so far. Okay. So this is not the case when it comes to non-abelian gauge theories. Non-abelian gauge theories is different. Non-abelian gauge theories. Why? See here, the only vertex in this theory is this one, right? So it's just a very simple interaction. But in non-abelian gauge theories, in addition to, let's say, quark-quark gluon, there's also a gluon-gluon self-interaction like this. There are gluon-gluon cubic as well as quartic self-interactions. So if you all put it all together, the beta function in non-abelian gauge theories can have a negative sign, and it looks like this. What is it? I have forgotten to write it down. So it's written in many different places, but not where I want it to be written. So non-abelian gauge theories. Okay, I'll write down the exact one later. So here the beta function beta G is well, I forgot to write it down. So you can find out. It's there in Griffiths also. He doesn't call it beta function, but it's there. Nevertheless, it will also be something that goes as G cubed. So that's the key thing, that the one loop beta function in these cases go as G cubed, whereas here it is going as lambda squared, which is also fine, we don't care. But we are more interested in theories of this kind. So let us try to do an integration of this thing, which of course Durba did the other day, but let's do it one more time so that we understand thoroughly why the solution looks like what it does at the one loop level. Okay. So now with beta E equals E cubed by 12 pi squared and beta G equals mu dG by d mu, where this thing is an energy. Okay, mu is an energy, carries the dimensions of an energy. So let me write this as mu dE by d mu. In fact, there is no partial derivative needed. Let me write this as dE by d mu. dE by d mu is E cubed by 12 pi squared. Okay, so 12 pi squared dE by E is equal to d log mu. So let me integrate this, and I get 12 pi squared divided by 2 times minus 1 by E1 squared plus 1 by E naught squared is log mu 1 by mu naught. Now everybody check that I have made no algebraic mistake up to this point. This is very important to make sure that there's no algebraic mistake that we are making. So obviously this means that E1 is a value at the energy scale mu 1, E0 is a value at the energy scale mu naught. So 1 by E naught squared minus 1 by 6 pi squared logarithm of mu 1 by mu naught is 1 by E1 squared. Okay, no mistakes so far, I hope. So one way of writing a solution to this is 1 by E naught squared times 1 minus E naught squared by 6 pi squared logarithm of mu 1 by mu naught is 1 by E1 squared. So another way of writing this is, so you see, if you so look at this. So if you write this down, multiply by 4 pi everywhere, then the inverse of the fine structure constant evolves like a straight line. So in the second screenshot that I sent you yesterday, which you can look at, you will see the kind of solutions that you have. You can have a look at what I sent you yesterday. It's a 1 by alpha, okay? It's a 1 by alpha is a straight line at one loop, and this will persist irrespective of whether it is QED or whether it is a non-abelian gauge theory, because there also it is going as G cubed. The functional dependence is still going as E cubed. Of course, here the beta function has a positive sign, there the beta function will have a negative sign. So in the case of an abelian theory, 1 by alpha will be a straight line that is rising as a function of energy, whereas for a non-abelian gauge theory it will be falling as a function. So that's the reason why in the 3 lines that I sent you yesterday, one of them is increasing and the other 2 are falling. Okay. Yeah. Yes. It means that this coupling constant is said to have a Landau pole, and that is what Landau had discovered long ago. Okay. But anyway, let me finish this and get the solution as we saw it. So if I multiply and divide and so on, you will find one way in which results are always given in textbooks is alpha 1 squared is given as alpha naught divided by 1 minus alpha naught by 3 pi. Now again things change. Here it is given as the square of the momenta m1 squared by mu naught squared. Like this. So this is one common way in which solutions are given. And young Nikshay here wants to know what happens if this thing, when will this thing become infinity? Okay, so you tell me, when will it become infinity? Yeah, please calculate it. Use Mathematica and calculate it. Get me the answer. Put it into Mathematica and get me the answer. Give me the numerical answer. Yes, please do. Yeah. That physically meant, according to Landau, that the theory doesn't make any sense. Perturbative theory does not make any sense beyond that energy. But we know, and there's a reason why I'm asking you to get that energy. Get it first. This guy is always asking me more questions than I ask him. It's all a test. It's like God has sent down some people to make me a better person. So. Thank you. Just a typo. That's a trick question. You have to solve it. There's only one scale in this problem. In QED, there's only one energy scale. What is that energy scale? Right, mass of the electron. So when you say 1 by 137 point whatever, It is in the Thomson limit, which is at the energy of the mass of the electron. So whenever I ask a question, at least I think that there is a reason why I'm asking that question. Okay. So he very quickly said that yeah, I'll plug it in and get the answer, but he hasn't done it so far. Okay. Obviously, it's a one loop result. No, it doesn't. This straight line business is only for at one loop. Yeah. Y equals mx plus c. That's all, as a function of as a function of log mu. Yeah. So if you see, I sent you that figure yesterday for a reason. I wanted you to look at the x-axis. What's on the x-axis? Well, on the x-axis is the log of the energy. Yeah. So it is a straight line as a function of the log. Okay. No, I'm telling you, you take mu naught as the mass of the electron. Yeah, square. So I want the square root of that. This is your problem number 4 in your homework set that was given yesterday. So you said 560. Square root of that. Correct. Times mass of the electron. Yeah. So what is the answer that we get roughly? Yeah, roughly at 10 to the power of 280 MeV, there is a pole. So the Landau pole is at 10 to the power of 280 MeV, which is a pretty large energy. And anyway, we know that long before this energy, there's the Z scale, then there's also the Planck scale. So evidently, you're not going to ask this theory to work beyond the Planck scale. That was the idea of Landau. You see, this was all 70 years ago when people started doing these things. People have a better idea about field theory. We know that you can put it on a lattice, you can do non-perturbative solutions. Some people like to do ADS CFT, other people like to do God knows what else. There are other guys like him who want to do StatMech. They have an idea of Wilsonian renormalization. They know how to do block, spin, this and that. So the picture is completely different compared to what Landau was doing. He was a pioneer. Okay. Still, what it does is it tells you that there's a fundamental scale beyond which this kind of formulas may not work. Okay. So it's a guide. It doesn't mean that it's the end of the story. It's very easy to say what problems are, but we don't know what the solutions are. Okay. It is. Yeah. Yes, of course. It is. It's just a guide. You know. Besides, today we know that something like UCD is the opposite behavior. Landau did his work when he thought all field theories must have positive beta function. We know that that's not the case. So you have a look at what I sent yesterday and tell me what I'm doing over there. What are the 3 different coupling constants that I have over here? Somebody explain what is the picture that I have sent you. You can Google for that paper of Utpal Sarkar and see what he has done and see what are those numbers and explain to me what I have done in that particular notebook. In this case, you read yes. Yes. Yeah. I don't know for sure. Yeah. I think mechanistically that would be the thing. But how do we know these renormalization? We have to take infinitely many of those perturbations. Nobody knows whether perturbation theory converges or not. In fact, we know that it doesn't converge. There is an argument which Leo, of course, has already studied. It's called a Dyson argument, which says that the radius of convergence of any of these series is 0. Nevertheless, it is still useful. It's used experimentally. You know, we are checking G minus 2 of the muon to very high orders. So mathematically, it may not be rigorously defined, but it's the only thing we have. It's the only game in town. We have no better way of doing things than this. You could, of course, try to solve it on the computer, but that's not really a solution, or it's not understanding. Is it? Okay, so please, somebody explain what's in that picture and what is being plotted, etc. Now, the standard model has three coupling constants. Okay, it has one for SU3 UCD, it has one for SU2 part of the electroweak, and then it has U1 prime or U1G prime that we call. But there's a peculiar factor of 3 by 5 over there in that particular calculation, which is used because this is embedded in all the three, SU3 cross SU2 cross U1 is embedded in SU5, which is a grand unified group for the standard model gauge group. And what it does for this particular calculation is it gives you a normalization for the length of the U1 generator. Okay. Otherwise, there is no natural normalization for the U1 generator. There is a natural normalization for larger groups because there is this identity that you have that lambda A, lambda B trace is equal to 2 times delta AB. But there's no such thing for the U1 generator unless you embed it into some other group, in which case it's the diagonal generator of that larger group. And so, but where do you see that over there? In the numbers that I have in that particular notebook, what are the numbers that I have over there which tells you about this 3 by 5 factor? 3 by 5 factor. Tell me, what are the three initial values that I have in that equation? Now, I have only given equations of straight lines over there, as you can see. Three straight lines which we later plot. So the first one is 58 point something. What is it? 58.8. And the other one is 29.85. So please take 5 by 3 of this and then add it to this and tell me what you get. .9. This is not quite 1 by 137. So these two things together, there's a relation between them which is supposed to give you 1 by alpha 1 or 1 by alpha of the electromagnetic coupling constant. So how is this number 127 related to 1 by 137? Right. So it has to evolve from 1 by 137. Rather, 1 by alpha has to increase. Rather, alpha has to increase from 1 by 137 to 1 by 127. 1 by alpha has to fall from 1 by 137 down to, yeah. So let's find the correct equation to do that. The correct equation to do that is 1 by alpha 1 is equal to 1 by alpha naught plus 2 by 3 pi times log of, let me see in my notebook what the equation is. See, while you people are watching cricket and IPL, here I am sitting and writing all these one loop equations, right? Log, no, actually it's a minus over here, by, yes, minus 2 by 3 pi logarithm of mu 1 by mu naught. So this is correct because this thing is 137 and then it has to decrease all the way, right? You agree? And where is this mu naught going to start? Mu naught, the starting energy, mass of the electron. Okay, so do it and tell me what you get at mz. Mass of the Z is 91. 91 what? And mass of the electron? 0.511. Yeah, let's keep 3 decimal places. MeV. Yeah. So put all that in and tell me what you get numerically. Excuse me? No, I'm not asking. I'm just asking you what is the value at Z starting with this formula. Put mu1 equals 92 GeV 0.5. Yeah. Z mass, because that's where this is being done. So he is getting 134, but we want a number like 127. Okay. So what's the problem? Why is it not working? Yeah, but still one loop ought to be reasonably good. Okay. So you people are being very naive because you're living in a world with only electrons, right? I mean, you're at 0.5 MeV and then there is 92 GeV. There are many more particles. So what happens? So each time you cross an energy where there's a new particle, that kicks in. So that will contribute to the beta function renormalization. The diagram that I erased. So this thing is between ME and mu. That's the only particle, right? It's the only degree of freedom. But as soon as you cross the muon threshold, there'll be one more contribution. Okay? So this 2 here will have to be multiplied by 2 beyond that energy. So you have to keep doing this. So you have to start mu, and then after this minus 2 times 1 plus 1 divided by 3 pi times logarithm of the next threshold. What's the next threshold? Actually, we can more or less say that the muon threshold is the same as the threshold for the quarks also, because we know that the pions also start getting produced at the same energy, right? Bit heavier. Since this is a log, it's not terribly sensitive, so I can turn on the quark degrees of freedom also. Okay, so let me do that. At the mu threshold, let me turn on the quark degrees of freedom. So what will be the contributions here to the beta function? How many quarks start to contribute? All the UDS, right? I mean, the kaon is 490 MeV, etc. So let's switch them on over here. So you have a 1 by 9 plus 4 by 9 plus 1 by 9. Okay, until we reach basically the tau threshold. So this is m tau by. So this is mu now. So we said that as soon as you cross the mu mass, then we have to turn this on. Then what happens at the threshold of tau? 1 plus 1. So one more 1 for the tau, plus 1 by 9 plus 4 by 9 plus 1 by 9. Now the tau and the charm quark are more or less the same mass. So we better turn on the charm quark also. That's 4 by 9. And let's go until we hit the B quark mass, m tau now, minus 2. Now there are no more leptons, but now the B quark has been turned on. 1 by 9 plus 4 by 9 plus 1 by 9 times log of mz divided by mb. Okay, now you put this in and now you tell me what's the answer you get. I'm not going to help you with any of these things. I'll take a nap for a few minutes. Now one of you go up to the blackboard and give all the parameters. Mass of the mu. Mr. Kirana, mass of the mu. Muon. No? Correct. Okay. not 5 really, 1 point, yeah, okay, 105. Okay, then mass of the tau, GeV, yeah. Mass of the B quark, no, that's charm quark, yeah. B quark, how many? No, right. Okay, so now you put this into your computer, now you tell me what is your value of the alpha that you get. Now this is only a crude calculation, okay, but still it had better give an answer that's close to that 127. Every single particle is a separate threshold. I just approximated the mu to be a threshold also for all the quarks. And because the charm quark and the tau are roughly the same mass, I've only used one threshold. Okay. See, these are all log corrections. So you just take, okay, there's a small region for running between 1.2, 1.7, no point in. So see, this is a kind of an art, how to approximate and to get an answer. Yeah. W. In principle we should, but it's too close to Z. Okay. Yeah, so he is asking a good question. We should also have a W plus W minus pair production. You're right, just that it's too close to Z, so we are just putting it. 30.7. Let me see what I've got. Okay, I've got something similar. Okay, so you see, so when somebody says, oh yeah, it's obvious, it increases from 1 by 137 to 1 by 128. You see, it's not that trivial and that obvious. And every single feature of the standard model spectrum has to be accounted for, even in a small calculation like this. That's the point that I'm trying to illustrate over here. Okay. And besides, you also learn to draw straight lines using Mathematica if you do these examples. Everything is in units of electronic charge. Okay. So if this is what it is for the electron, it's the same for the muon. So 1 plus 1 muon and electron. If it is a U quark which is running around, 2 by 3 squared. If it is a D quark, it's 1 by 3 squared. The reason for not spelling out everything is it has to become second nature to you. You know, all these things have to be at your fingertips. Yeah. See, the theory breaks down long before that. We know that you cannot have a flat space limit of QED anyway, you know, or even if you throw away strong interactions, if you throw away weak interactions, let's say the world has only QED, okay. We know that at 10 to the 19 GeV, there's already the Planck scale, okay. There's no quantum theory of gravity. So there's no point in trying to take a theory which is, long wavelength limit and then trying to take it to such asymptotic energies where you know very well that it cannot be a valid theory. Okay. Nobody is saying any such thing. We are just saying we don't have a quantum theory of gravity. That's all it is. We know that gravitons, whether we know gravitons have not been directly observed, but we know one of the predictions, which is gravitational waves, which have been observed now. So we know that this is one of the many predictions of Einstein theory. So what exactly is the question? Hmm.
In this series of particles that
Hmm.
do we consider gravitons to be there?
They are so weakly coupled, right? So natural coupling constant there is Newton's constant, and it is so small that there's no way in which it's going to add to this. You know, it's one more coupling constant. It is true that you may have a loop of gravitons that is connecting to a photon, and it does contribute to the beta function, but that is subleading by so many orders of magnitude. So it's just not. I mean, ultimately everything is limited by experiment, right? If you are only measuring things to 10 decimal places, and this is going to be a correction at the 40th decimal place, it's not going to be visible, right? Yeah. Yes. No, we are not saying it's the loop. In that particular notebook that I sent you, the value of 1 by 127.9 is introduced as the value of the electromagnetic, the fine structure constant at the Z scale. This is only a scale at which it is introduced. It has nothing to do with Z being charged or not. Just an energy scale, 91 GeV. Okay. Hmm. Yes. No. No, in a sense, yes, because the Z also couples to the electron, right? I mean, it's a neutral. So Z couples to everything. Z couples to neutrinos, nu bar, E bar, through G sine theta W, whatever. Not the electromagnetic charge, but the other one, the G. G and the G prime. It has a G prime also. Yeah. Hmm. Yeah, it's not coupling to the photon. Yes. Yeah, you're right. Yes. Even through loops, it can. So this thing here, it can produce something like this and then produce. So there are also these issues of mixing of Z, and then you have to re-diagonalize and all that. I don't know. I can't immediately answer that question. Yeah. You can have some kind of effective theory where you can have at one loop and then it's non-renorm. Now we have techniques to handle such non-renormalizable theories also.
If some like we know neutrinos are there, but we don't consider neutrinos in this type.
It depends on the context. Depends on the context. Not because of mass, because the coupling constant is not there for neutrinos. I don't want to introduce anything new today, so I more or less wanted to stop here and wanted to deal with these things. And I have, of course, other things, but I don't want to start on it today. I wanted you people also to get a break. Otherwise, this non-stop, grind every Tuesday and Thursday is a bit too much. It's too much for me. I don't know about you all. So I'm not going to talk about anything new today. But if you want something you want to discuss, we do it, or we just stop. Okay. Yeah. Yes. Yes. It's the presence of this additional couplings, or the additional self interactions. So it's the nature of the vacuum. Like we talked about screening over here. So it is a process of anti-screening. So since you like condensed matter physics, there are analogs of paramagnetic and diamagnetic media. One of them is one and the other is the other. Okay. So there are parallels from there. It's very nicely discussed in the book of Cheng and Lee. There's a section where this magnetic properties of the vacuum are discussed, where they explicitly talk about this. Those are all good undergraduate projects to go back and see how they work, because it connects many different subjects. Anything else? Yeah. Yes. I haven't yet got to it. I will do it. Yeah, but dynamical, I don't know. But I'll definitely, of course, talk about the Higgs potential and all. what we are talking about here is always in the loop expansion. There are beta functions for the full theory, which is all the Wilson and so on, which is beyond the scope of this course. So yeah. So there's a beta function in the lattice, there's a beta function that's used by condensed matter folks. So it's a big playground of ideas. So here we will be only talking about beta functions. Okay, so please do all the problems that I give you, otherwise there's no way you can, keep up with the material that is being discussed. Next week we meet only on Tuesday because I'm not here on Thursday. That was the reason why I did those classes on those holidays. And I also took one of Sudhir's classes because I was going to lose one class. And next month also probably one day we will miss class. But apart from that, I think we are pretty much on track. So I would now say that except for the last 2 chapters of Griffiths, virtually the whole book has been covered. Of course, I cover it bit by bit, little pieces here and there, but it's enough for you to be able to go through the entire book, especially if you use resources like Romao. You download his notebooks, you learn to run all these cross sections. It will come to you easily, but you have to put in that effort. Okay? Have you done it? Romao books? You've done them. See? Yeah. Those of you who haven't, you ask him. He will teach you.
When we consider the Higgs field, potential, we say that so that theory is denormalized.
Yes. Yeah.
So you're saying we are dealing with this denormalization with this point of view.
Yeah.
So we not also consider the 5, 6 or higher terms. Then it will not be denormalizable.
These are engineering models. What's the name of this course? This course, the name. Model. So the word is a model. This is the model that we have accepted as something that we work with at the stage whose properties we are still checking. And we may check for the next 10 years, 20 years, 40 years. And it may break down at some point. Where it will break down, how it will break down, we don't know. This is the simplest possible potential which was introduced by Weinberg, and it worked. It gave the correct masses for the W, gave the correct masses for the Z, gave the correct mixing relations, and there are n different tests that some of you are going to do, various electroweak tests based on this model. Okay, one of you or some of you are going to do the Higgs, where you will test the various features of this model. Okay, you don't like the model and it breaks down, that's fine. But exactly what is the new thing that will replace this model will be something that we have to work on. See, if everything is already done, there's nothing for us to do, right? So we accept this as a model, we work with this model, we test it, we see how it breaks down. Then you may say, oh, Mr. Chugh says Weinberg is no good, there had better be a 5 to the 6th term. Then you add it. Then you have to propose tests for your model. You have to tell LHC what to search for to test your model. Okay, so that's how this business works. And it's the same in anything. If it is in biology and you think that there's a crab that is eating a fish, and you say, how do I know the fish is not eating the crab? You have to propose a test for that. Okay, or in chemistry, you add 2 compounds and you say get a 3rd compound. Say, no, I must get some other compound. You better propose it and you better detect it in your laboratory. Okay, it's okay, we'll decide if it's absurd after the question. Yeah. Yeah.
Let's say you have 10 dimensions, 4 important dimensions, 6 of them are covered in the pattern. So at those points, may be denormalizable for higher order.
Right.
So do we consider that if we try to do this standard model business in string?
You could. It's not. See, string scale is very far away. We are just barely at 1 TeV, where LHC is able to push the boundaries 500 GeV, 700 GeV. But you may already start getting corrections. You can introduce effective operators consistent with the standard model, which may make predictions not given by the standard model Lagrangian per se, but some changes to the standard model Lagrangian. It's the same thing. You have a problem, you want to solve it, you introduce something. When you introduce something, it's going to make some predictions which you have to either verify or you have to falsify. You either have to rule it out, you have to confirm it. It's like anything else, right? Why was it absurd?
String theory, I couldn't expect same symmetries to be there in string theory.
We don't know. It's a very ambitious model, so which is at a much higher scale. And then you say that you have to cross 15 or 17 orders of magnitude to do it. If you want to make that theory work and make it sensible and make it, useful, then it is the onus is on them to make it useful and sensible and verifiable, falsifiable. Okay, so I think I'll stop recording. Anything more? Anything more? Yeah. Well, confinement is observational. We have never seen colored quarks. We've never seen colored gluons. But it's not been proved in the sense you can't start with the QCD Lagrangian and then show that the bound states must be what they are. It's partially at very high energies, yes. Yeah, free in the sense that, see, again you have to ask what is meant by that. So when we do deep inelastic scattering, it is a very particular way in which quarks behave as if they are quasi-free inside a proton target. Okay, so it doesn't mean that they are free per se, but what you will see is that the cross-section formula that you get is like an incoherent sum of scattering over individual point-like constituents. That is the only statement. Okay, that they are actually deconfined is a different statement. That would be at very extreme conditions like very high temperature, high density during the Big Bang era, or specific laboratory conditions like LHC in the ion-ion collision mode, or in one or two other experiments you have a quark-gluon plasma. Even there, of course, there's a plasma, but it rapidly cools and hadronizes. Okay, so there's a time or a small period where they are behaving as if it's in a plasma state. Okay, I don't know whether I answered your question, but that's the answer that I have to your question. Okay, so nothing more. I'll stop recording. Yeah, what is